Hello, good morning. I hope you are well. Please, if you can hear me, I have just added a message, an announcement. If you can like it, okay. Think that I see that you can hear me. Many thanks. So we will continue today with the instructions of the instruction set architecture we are seeing. Remember, it's called LEG-V8. As always, remember, part of the material shown in these slides is taken from the book. So we are going to see how the instructions we saw yesterday are actually represented in the computer. So yesterday we saw instructions in assembly code, and now we are going to see how those instructions are converted and represented in the computer. We will also see additional operations like logical operations and conditional operations. So let's start. We have mainly three different types of instructions in LEG-V8 instruction set architecture. So these instructions are encoded in ones and zeros, in bits, in binary, and this is what we call matching code or matching language. So for the instructions, remember the add instruction, the sub instruction we saw yesterday, we refer to those instructions as assembly instructions, and once those instructions are actually converted to zeros and ones, which is the language that the machine understands, we call this matching code or matching language. In the case of LEG-V8, all the instructions are encoded as 32 bits. Remember, we also saw yesterday that 32 bits, we call this a word. We are going to see three formats of instructions. The reason for having LEG-V8 a very small number of instructions, and all of them having similar formats and having a limiting number of registers, this is because of making things regular. Why do we want to make things regular? Remember, we have also seen one of the design principles, which is make things simple, because this helps to do things in a regular manner. And this is something that motivates many of the decisions for LEG-V8, and remember that LEG-V8 is a subset of ARM-V8. So keeping all those instructions 32 bits, remember that we have for all the arithmetic operations 3 registers, the destination and the 2 inputs. All these things makes things simple, and this helps to have regularity. So let's see the first instruction format, which is called R format. So R format instructions is the R comes from register instructions. We saw yesterday some of those instructions. The add and the sub are instructions because they work on registers. So the instructions fields of this instruction format is the one we see in the screen. So first of all, we have an operation code. Remember yesterday we saw a couple of operation code. We saw the add and the sub. So this will be represented here by 11 bits. Why 11 bits? Because the designers of LEG-V8 decided it having 11 bits. Why we place the operation code in the beginning and not in the end? Because the designers decided to have it that way. The next field of this instruction you can see here is called RM. Everything starting with an R refers to a register. For this we have 5 bits. Why 5 bits? Because remember that in LEG-V8 we have 32 registers. So with 5 bits we can refer to any of the 32 registers. In this case, RM refers to the second register of the short operand. For instance, we will see this in an example later, but remember in the add instruction we have a destination register and 2 input operands. So this RM will be the second register operand. The M is just something the designers have decided to put here, so it doesn't mean anything. They can have here any letter. Then we have this field shift amount. For this kind of instructions, for R format instructions, this is going to be just 0. Then you may be wondering why we have a field here that is going to be 0. Because the same format will be used for other instructions types, and that's why we want to make things and we want to make things regular. And for doing this sometimes we need to lose some bytes, as this is the case now. So this field is not used in this format instruction. Then we go for Rn, which is another register input. In this case is the first register input. And finally we go to the Rd, which is the register destination. All the registers, as I have explained, are represented with 5 bits because, as I have mentioned, in LEGVI we have 32 registers, and with 5 bits we can refer to any of those 32 registers. So let's see an example now. I have put colors here. So remember one of the instructions we saw yesterday. We saw yesterday the add instruction. So the operation code is the add. So this add will be here. And then we need to read this from right to left. So the register destination is here. The register input number 1, Rn, is placed here. And then, as I have mentioned, shift amount is not used in this instruction format, and we go for the second register input. Okay? So let's see this with a real example. Imagine yesterday we saw this instruction, which just adds the value of register 20 and register 21 and place the result in register 9. Okay, so how do we convert this assembly instruction into machine code, into ones and zeros, into the language that actually understands my computer? So the machine code equivalent for this instruction is the following. So here we have values in decimal. So in this case, the register destination is register 9. So we just place here a 9. And then LEGVI will know that if we have here a 9, this means that the destination of this operation is going to be put in register 9. Okay? And we do the same for the rest of registers. The first input register, Rn, in this case is register 20. So we just place here a 20. And for the rest of the data, we have seen the shift amount in this case is 0 because it's not used. And the second register input is 21, the register in blue here. We just place here a 21. And then the operation code, for the time being, we are going to assume that I'm telling you that the operation code for the add instruction is this number. Why? Because LEG designers have decided it's this number. I will show you later how to look for the operation code of any other operation. So now, notice that all this is in decimal, using decimal. This is just for the sake of clearness. But actually, the computer what understands is zeros and ones. So if we convert 9 to binary, we have this number. If we convert 20 to binary, we have this number. If we have convert 0 in binary 0, but we need to fill the 6 bits, so we just fill it with 6 zeros. If we want 21 in binary, we have this number, and the same for 1112. Okay, so this will be the matching code equivalent to this instruction here. So now you have seen how the instructions you write in assembly language, how they are actually converted in the language of the computer. So this is what the computer is going to read, and this is what the computer is going to analyze. And thanks to the format that we have designed and we have defined, the computer will know in which place is each register and which operation to perform. Sometimes, in order to make this easy to represent, some people, instead of using the binary or the decimal notation, it just uses the hexadecimal notation. This is just for making it simple to move in operations. But in the end, the machine, what is going to understand is zeros and ones. Okay, makes sense? So what we have seen here is, remember, in the first lecture, we saw that we have different levels of program code. So the high level, we have it in the top, was like C programming, Java programming, or any other programming language you want. I am putting here an example. The next level is the assembly language program. In this case, we are using LegVA, and we have an instruction here which is represented this instruction in high-level language is represented by this assembly language instruction. And now we know that this instruction is converted to this matching code. And this is what actually the computer understands, and this is actually what the computer receives. All the layers upper these zeros and ones are just abstractions. And remember, why do we use abstractions? Because for us, for humans, it will be very difficult to work with ones and zeros. But if working with assembly language, or even better, working with high-level language is more productive and more easy for us, because it's closer to our scientific notation and to our spoken to the language we speak. Make sense? So now I would like to show you how do we actually look for the operation code. In this case, I have told you that the add operation code was 112. Remember that I told you yesterday that we have a reference data in the Canvas module. We have here, you see, a reference data PDF. In this reference data PDF, you can see I have here a screenshot of that reference data PDF, and we see here the add instruction. So the add instruction, we have here a field which says that the operation code for this add instruction is in hexadecimal 458. So then, once I know the code in hexadecimal, I just convert that code, in this case in decimal, and also in binary. And by doing this, I get the operation code of an instruction. I'm going to repeat that again, okay? So I go to the reference data sheet that you can find on Canvas. Here, in this PDF, you will have all the instructions. One of those instructions is the add instruction, and in this instruction we see that excuse me, the operation code is 458 in hexadecimal. If we convert this value to decimal and to binary, we have the actual operation code that the in matching code. Okay. Okay, let's see another type of instructions. All the format instructions work in the same manner. So remember yesterday we also saw, apart from the add and the sub, which were arithmetic operations, we also saw memory operations. In this case, for memory operations, which were the load and store, you remember, we have D format instructions. The D stands for data transfer instructions. So as I have mentioned, those usually refer to load and store instructions. So the first, the operation code is as before, so we have 11 bits for the operation code. Then we have a field which is the address. This address is the base address for the memory address I'm accessing. Remember yesterday we were accessing an array A. So, and we have the base address of this array A in a register called x22. So this will go here in the field address. Then we have another 2 bits field which just expands the operation code. We will see later how this works. Then again we have 2 registers. Rn is the base register and RT is the destination register in case we are loading some data from memory, and if we are storing data from memory, RT will be the destination register. We will see an example now, and it will be very clear, so no worry. The reason why we have this different formats but all with similar structure is that we want to is also one of the design principles. We want to keep all the formats as similar as possible, and if we change the size of the operation code, the size of the address, and so on, it will make things more complicated. So that's why in LegV8 and also in ARMv8 we keep the instructions 32 bits, and even here that maybe you could say, okay, maybe we can have here more bits for the address, but this is just in order to make things more regular. We have just 9 bits, so we are only using 9 bits. And this is because at some point we need to decide, we want to have more bits for addressing memory, or we prefer to have all the instructions with the same length. In this case, it was decided having all the instructions 32 bits. So let's see an example. So here we have the D format instruction, the format for the D instructions. So opcode will be, in this case, load, a load instruction. The address, in this case, will be here, okay? Register with the register with the for the base address will be here, and then the destination for the load will be here. So as you could see here, we have an example. So in this case, we are loading in the register 9 the value in memory starting at the base address contained in register 22 and plus an offset of 64. Remember that this 64 is like accessing to the element 8 of an array. Remember that it was an scale. So, and as we know that each address refers to 1 byte, so we need to scale it. Okay, so I would like to propose you now an exercise. I would like, you have seen how I have converted the R format instruction into binary code. So what I ask you is, would you be able to get the matching code of this instruction here, the load x9, x22, 64 in binary code? So remember, you can use the reference data sheet that we have here. Okay, so using that, using what I have just shown you in the slide for the I format, could you be able to convert this instruction to matching code? So I give you 2 minutes. Okay, so good luck. Okay, so time is over. Hopefully you have time to solve this. So I'm going to show you now how do I achieve this. So in this case, we see that register T, okay, X9, we just place here a 9. This is just as before. For register N, we have 22. Register 22, we just place here a 22. Operation, this is going to be 0 right now. And then for the address, I have here a 64. And it's the same, I just place here the number 64. For the operation code, this is something I hope you have done. So I just go to the reference data sheet that you can see here, and I'm looking for an instruction called LDUR, the load. So we have here the load instruction. Can you see it? Yeah. And we see here that the opcode for this instruction is TC2, 7C2. Okay, so this is in hexadecimal. So what I can do, if I'm a very lazy person and I don't want to convert this on my own, what I can do is I can open a calculator. Here I'm using Windows. I know that for Linux and MacOS you have similar things. So here the calculator, you can choose the programmer calculator, okay? I just click here, this button here, and I have here the programmer calculator. If I'm in the programmer calculator, you see here that I have hexadecimal, decimal, octal, and binary. If I click hexadecimal, then I just input this number in hexadecimal, and automatically I have the number, equivalent number in decimal, and the equivalent number in binary, which is actually what I have placed here. Okay, so this operation code, I have looked into the LEC reference data. I have seen that the code for this operation is 7C2, and I have just converted this hexadecimal into decimal value, which is 1986. Make sense? Once I have done this, I have all the information I need for converting my instruction into matching code. So the matching binary code for this is, as I have mentioned, you can just convert those decimal values into binary, but using the calculator. This is what I have actually done, and with this I got this matching code, which is the actually matching code in binary for this instruction here. Okay, it's very similar to the add. We are only changing the format of the instruction and the operation code. So the machine, once he is processing all these instructions, the first the machine will do is looking at the operation code. By the operation code, the machine will know, oh, this is a D format instruction. So he will know that in this place here there is an address, and in the registers are in the last two fields. If it is an I format instruction, he will look for other places for registers. So now we are going to see the last format instruction. Is the I format instruction. In this case, I refers to immediate instruction. Remember, the other day we showed that apart from the add, we have something called add I, which was for adding immediate values. In this case, we have the operation code as always, and then we have the register destination, the register input 1, and then what we are going to add to this register destination 1 is an immediate value, a constant value, 0, 1, 2, 3, whatever we want. Let's see an example. So here we have, again, the operation code, in this case for the add I instruction, then register destination, in this case here, register input 1, Rn, which goes here in yellow, and then the immediate value. And I have also added an example here. In this case, we are adding 1 to register 9. Okay, so now I'm asking you a similar question than before. Could you convert this instruction to decimal code? I give you again, instead of 2 minutes, I'm going to give you now, let's say 1 minute, okay, starting now, to convert this instruction into matching code. Okay, so time is over. And what I have done again is something similar to what I did before. Okay, I have just gone to this my reference data, and I have searched for the operation code. But now I think that you probably had problems with this number. Okay, what happens here? If we go to the reference data sheet, we see that there are some problems with this number, because if you remember, in the previous format operations, we have here 11 bits for the operation code, but here we have only 10 bits. So from where I got this number? Because the rest of the numbers, I guess, are clear. So here register 9, I just put a 9. Here register 9, I just put a 9. And here immediate value 1, I just put 1. And then converting this to binary is obvious. But from where I got this number? So as I have mentioned, in R format and D format instructions, we have operation code of 11 bits. But here, designers have decided to have only 10 bits in order to have room for larger immediate values. So for having here 12 bits instead of 11. So what happens then? That for the add I operation code, we have this number here in hexadecimal. Okay, we have two numbers. Why we have two numbers here? So we have two numbers because we are indeed saying that any operation starting by those 10 bits will refer to an add I, and if and that means that any operation starting with those 10 bits, it doesn't matter if after those 10 bits we have a 0 or a 1. It will refer to an add I because there is no other operation starting with the same values, because we have log all the values, the two values in this case, starting with these 10 bits. Okay, makes sense? So in this case, we have an operation code of 10 bits, and for doing that, we need to make sure that there is no other operation starting with the same 10 bits. Which number starts with the same 10 bits? 488 and 489. So we log all these operation codes, so no other instruction can have either of these operation codes. And that's why we get an operation code of 10 bits by logging two operation codes of 11 bits. Make sense? Yeah, so remember in the same reference data, you have also this operation code in binary. So here you see for the add I, you have this in binary, and you see that it's also 10 bits. And for the add, which is in the upper row, we have 11 bits. So, and here is what I have explained of the two values that we are logging for the add I. For the add, we only log one value because the operation code is 11 bits. Here? Okay, so with all these format instructions, we come to we now can see how instructions are stored in the computer. So instructions are stored the same way as data. Everything is placed in the memory. So in the memory, I can have, for instance, here I can have the source code of my C program in an editor. I can have a Microsoft Word program. I can have a book test. I can have also the matching code and everything. Everything will be in the same place in memory, and everything will be represented by zeros and ones. So this gives us the concept which is called a stored program computer, which means that a computer stores programs, program instructions in the same manner as they store data. They store everything in memory. You have here a more complete definition, a more formal definition of stored program concept, and it's something that you will find at some places. And it basically refers to the idea that everything, instructions and data, everything is stored in memory and is accessible from there. So it's stored in the form of zeros and ones, not only the data but also the instructions. And you know now how those instructions are represented in zeros and ones. Okay, so right now we are going to see some more operations. So in this case, we are going to see logical operations. So logical operations, you have seen these operations in the network part. We have shift, left and right, which in LegVI you have here the equivalent for this logical operation in LegVI. So for shift left, we have LSL, which stands for logic shift left. This will be logic shift right. And then for and immediate, we have these two instructions in LegVI. for the OR logical operations, we have OR and OR immediate, and for doing the node, the negation, we are actually using an exclusive OR. So those instructions can be useful for manipulating bits, for manipulating bits. And let me show you before, for instance, how we can use the shift instruction, logical instructions to multiply and divide numbers. For instance, if I have this number, so here the number is in binary and here the number is in decimal. So if I shift left by 1, which means that I move the initial one to the left by 1 position, is the same as multiplying by 2. Okay, if I do the same but shift left the first one by 2 positions, so from here to the second position, so it's like multiplying by 4. So you see here how do we get the multiplying value regarding the related to the number of positions I shift left. It's just the power of 2. It's just 2 to the power of the number of positions I'm shifting left. If I do these 3 positions, so if I shift left 3 positions, is like multiplying by 8, which is 2 power 3. Okay. So the opposite, shifting right, will give us the division. So in this case, if I shift right by 1, it's like dividing by 2 power 1, which is 2. If I shift right by 2, it's like dividing by 4. And if I do this by 3, it's like dividing by 3. Okay, so shift left, multiply, shift right, divide. So here you have a kind of summary. Okay, these operations are useful, as I have mentioned, for multiplying and dividing. Then let's see how these operations are represented in machine code. We use a format we have already seen, the R format, the register format. So they have the same format as the add operations. We just have a different operation code, but the rest of the registers of the fields are the same. But here we are going to use this field, the shift amount, that we were not using before. So in this case, you see that instead of using the second input register, we are using the shift amount field, which is placed here as an immediate value. So with this operation, we are saying, okay, shift left the content of register 19 by 4 positions. Okay, this is what I have just explained. Make sense? I think that you have already seen all these logical operations in network lectures. So you have here this in this slide just for you, but you have already seen that in network lectures. So what I'm interested here is to show, I think that you have also probably seen this for networks, but I'm going to repeat this here. So for instance, we can use an AND instruction, which has an R format. We have already seen this format. And in this case, the AND instructions will be useful for to match some bits in a word. For instance, you see here that with an AND, only when we have a 1 in X2 in register 10 and a 1 in register 11, we will have a 1 in that position in register 9, which is actually what is happening in these 2 bits. In the same manner, we have the OR operation, which could be useful to include bits in a word. You know that for an OR, we get a 1 in register 9 if either X10, if either the bit in register 10 or in register 11 is 1. So you see here that we have 1 in all those cases. So we only don't get a 1 when we have 0 and 0 in register 10 and in register 9. And finally, we have the exclusive OR, which is similar to the OR, but we only get the value if we have a 0, if we have a 1 only in one of the two input registers. So if the 1 is in both registers, we got a 0, but if we have 1 in only in one of the registers, for instance, here we have a 1 only in register 12, but not in register 10, we have a 1 in register 9. As mentioned, I think you have already seen all of this in networks, but I'm just showing you here how this is expressed in LegVI. So then finally, we are going to see a very important type of instructions, which are the conditional operations. It could be seen as instructions for making decisions. So we have mainly 3 different instructions for making decisions. So the first one is called CB set, compare branch if 0. So this is a new format, CB format. And what we have here is a register and a label. What this means? So this means that if the register in this, the value of the register we place in this position is 0, we will go to a place which is labeled with label L1. Okay, compare branch if 0. Similarly, we have compare and branch if non-zero. You see the N here. So in this case, if the value of this register is not 0, we will branch to a place in the code where we have label L1. This instruction has also CB format. And then finally, we will have an unconditional branch, which is always, once you read this instruction, branch to label 1. So regardless of any result, you always branch to a label L1. Let's see an example to make this more clear. So for instance, I am showing here the code for a loop. So we have here an add immediate. So I'm adding to register 22 the value of register 0, which you remember, this is register 31, which is always 0, okay? And we are adding the immediate value 10. You have here the comment what these instructions mean. So we are saying here that register 22 is equal to 10. And then we have here loop, which is a label. We have here a sub-immediate instruction, which is just subtracting 1 from our register x22. So if it had 10, after this, the first iteration, it will have 9. So what we do here? So after subtracting 1, we check, okay, is register 22 equal to 0? So compare and branch if 0. So if is register 22 equal to 0? If yes, we go to a place, to a label called exit, which is actually here and which is doing nothing. And if not, so what happens if x22, register x22 is not 0? So we don't go to label exit. We just continue with the execution. In this case, the executions goes to this other instruction, which is a branch instruction, which says that we branch to a label loop, and in this case label loop is here. So we will be doing like a loop here, subtracting 1 from register 22. So in the first iteration it will be 9, 8, 7, and so on, and at some point register 22 will be 0, and once it is 0, we will jump to label exit and we will finish this example. I give you some time to look at this example. Okay, It's clear? So if you remember, I have told you that this instruction here, the compare and branch if 0, has a CV format. So if you go to the reference data, you see here the instructions and the instruction format. I have shown you the R format, which is the register format, the immediate format, the data transfer format, and here we have also the two instructions we have just seen, the V format for the branch instruction and the CV format for the CV set and the CVN set format. So you have here the format for these instructions, and they were similar to the ones we have seen. Okay. So let's summarize what we have seen in this lecture. We have seen how actually the instructions we learned yesterday in assembly language, how they are actually represented in the computer in zeros and ones. We have also seen some logical operations, how they are represented in LegVA, and we have also seen some conditional operations which are very useful for doing loops and these kind of things. In the next lecture, we will see something called procedure calls, which are similar to the functions we have in programming languages. So now we have some minutes. I will try to see if you have any question here, and I will try to address some of those questions. So someone is regarding the practicals. So every Wednesday you will have at 1 p.m. I will publish the lab for that week. So then you will have time for doing this lab, and then every Friday I will publish the solutions for this lab. And together with these solutions, I will also upload a video explaining the solutions for that lab. So our labs assess, they are not individually assessed, but remember that in the assessment in week 13, you will have questions from both lectures and labs. So everything will be assessed at the end. So as I have mentioned, today at 1 you will have the first lab. It will be very easy, and it will be basically you will be working on what we have seen. It's something to support all we have seen in the lectures, and it will. I'm sure it will answer a lot of your answers. Okay, so Wednesdays at 1 you have the lab published, and Fridays you have the solutions with a video covering the solutions. Okay, I'm going to look for more questions. So someone is asking for addressing types. We will see addressing types in next lecture. So I'm not interested in that now because I'm going to explain that in another lecture. So someone is telling, where can I download this PowerPoint? So this PowerPoint, as I already mentioned that. So if you go here, I have placed here a PowerPoint. The only difference with this PowerPoint and the one I'm showing you is that it doesn't have the solutions for the questions I asked you online. For instance, I have asked you online, please, can you convert one instruction to matching code? So I don't have that solutions here. And now I will upload them after the lecture. I will upload them. So for instance, for yesterday lecture, you see that I have slides after lecture and slides before lecture. Okay, so these ones here are slides before lecture, and once we finish this lecture, I will upload the slides you have actually seen. Okay. Okay, so thank you very much for your attention. I hope you have learned something. I hope things are getting more clear every day, and I'm sure that with the lab you will have everything more clear this afternoon. So thank you very much for your attention again. Have a nice rest of the day, and remember, if you have additional questions, you have the ticketing system, and we are here to help you. Okay, thank you so much. Bye bye. See you. Bye bye.